Welcome back to our final lab lesson topic on dynamic simulation. In Lab 4, we learned how to create fully constrained assemblies in Inventor, but for mechanisms like the door hinge and the gear train that we looked at, we don't necessarily want to fully constrain all degrees of freedom, because these devices are intended to move. In Lecture 5, we talked about how we can use assembly constraints with limits and motion constraints to allow constrained movement in an assembly, and we also discussed creating a dynamic simulation in Inventor to simulate our mechanism. So we are going to do this for our door hinge assembly in this video, and then for our gear train example in an accompanying video. With our door hinge, our goal will be to replicate this animation, where the pin translates 5 inches into place in the first second, then the hinge closes in 1 second, then stays closed for 1 second, reopens in 1 second, and finally the pin translates back out 5 inches in 1 second. To accomplish this, our steps to make a dynamic simulation will be as follows. First and foremost, we need to make sure that we have a well-constrained assembly with either assembly constraints with limits or motion constraints that will enable specific movement. Once we have a constrained assembly, we can enter the dynamic simulation environment to create a simulation. In some cases, this may require inserting joints that describe the motion relationship between components, and then imposing a motion on a joint to make something happen during our simulation. Then we can run the simulation in Inventor and review output graphs of positions or velocities of our joints from the simulation. So let's walk through these steps to make our door hinge simulation. Recall from Lab 4 that we fully constrained our door hinge by applying an insert constraint to the pin and a couple mate constraints and an angle constraint to the hinges. Now we want the pin to be able to move, and we also want the top hinge plate to be able to rotate, so we are going to have to make some adjustments to our constraints. If we find the angle constraint applied to the top hinge plate and edit it, we can see that it is currently constrained to an angle of 180 degrees. But now we want it to be able to rotate from fully open, which would be 0 degrees, all the way to the current 180 degrees. If we click the double arrow drop down in the bottom right edge of the constraint window, we can change this assembly constraint to an assembly constraint with limits, where we specify the minimum angle constraint of 0 degrees and the maximum angle constraint of 180 degrees. Now this will allow the restricted motion that we want for our hinge. If we check off the resting position radio button, then the assembly will return to the original angle we specified after we stop dragging it around. Cool. Now, we are able to do the same thing with our insert constraint for the pin, where we can apply limits of 0 and 5 inches to define the restricted linear motion of the pin. But this actually won't generate a joint for us when we go to the dynamic simulation environment. So we are going to delete this insert constraint and replace it with a few alternative constraints. An axis-axis mate constraint, an angle constraint locking the rotation of the pin, and finally, a face-face mate constraint to lock the bottom face of the pin head to the top hinge. Rather than just leaving it at that though, we are going to specify the 0 to 5 inch translation limits on this constraint so that our pin is still allowed this constrained movement. So we've applied 2 assembly constraints with limits for this example, which allows individual components to retain some ability to move. In this case, our components move independently, but in some cases we have mechanisms where the movement of one component imposes motion on another, like with a gear train. In these instances, we will need to apply motion constraints to define the motion ratio between components, and we will see this in the gear train example. For now, we have a well-constrained door hinge, which means we are ready to enter the dynamic simulation environment. To do so, go to the Environments tab in the Inventor toolbar and click on the Dynamic Simulation button at the very left of the toolbar. This will bring up a new set of tools in our toolbar specific to the dynamic simulation environment, as well as a new dynamic simulation browser showing the joints associated with our assembly. It's important to understand that there are 2 modes in the dynamic simulation environment. The construction mode, which enables you to do things like insert or edit joints, and the simulation mode that allows you to run a simulation and view the results with the output grapher. So we want to be in the construction mode initially in order to set up our simulation. If everything in the browser is grayed out, this means you're in simulation mode and you need to click this construction mode button in the simulation player to get back to construction mode. If you close the simulation player by accident, you can always bring it back up by pressing the simulation player button in the toolbar. So we are now in construction mode, and let's take a look at our standard joints that we have in our dynamic simulation browser. Standard joints are generated based on the degrees of freedom remaining between components in our assembly, and three types are prismatic, revolution, and cylindrical. A prismatic joint is like our hinge pin joint, where there is one translation degree of freedom, since our pin is allowed to move in and out of the hinge. A revolution joint has one revolution degree of freedom, with an example being the joint between our two hinge plates, where the top hinge is able to rotate between 0 and 180 degrees. Finally, a cylindrical joint has both one translation and one rotation degree of freedom. If we went back and deleted the angle constraint that is currently locking our pin's rotation, and if we re-enter the dynamic simulation environment, we'll see that our prismatic joint becomes a cylindrical joint because the pin is now able to rotate as well as translate. Okay, I'll just put this back now. If we hover over a joint in the browser, we will see two sets of coordinate axes appear on our model, representing the two coordinate axes used to describe the joint. The axis with one arrowhead is the x-axis, the one with 2 is the y-axis, and the one with 3 is the z-axis. If we want to edit this to change their orientation or their origin point, we can right-click and select Edit. For example, perhaps we want to reposition our pin joint axes at the end of the hinge and the corresponding bottom face of the pin head. In some cases, when we have motion constraints in our assembly, we will have to add additional joints related to those constraints. For example, for a spur gear train, we'd have to add a rolling cylinder on cylinder joint. For bevel gears, we'd have to add a rolling cone on cone joint, and you can look through some of the other joint types that are available. For now, we don't need to add any other joints, so our next step is to impose motion, which we will do by right-clicking on the joint of interest and selecting Properties. Here I've clicked on the pin prismatic joint, and if we go to the Translation Degree of Freedom tab, T stands for Translation, then we can see the current position of our joint in our model, which is based on the coordinate axes of our joint that we selected. So you can always edit the joint origin and axes if you want your baseline position to be a specific value. With the way my coordinate axes are set up, the 0 position will be when the pin is fully inserted into the hinge assembly, which is good. Now we came to this window to impose motion, so we are going to click on this rightmost button, Edit Imposed Motion, where we can now check off Enable Imposed Motion, and then we can go ahead and specify what the imposed motion will be. We are going to specify a piecewise function for a driving parameter, and our choices are specifying position, velocity, or acceleration. In this case, since we know the desired position of our pin over time, we will check off position and click on the graph icon to open another imposed motion window. In this window, we can generate our piecewise position function by double-clicking on the graph to add points, and then clicking between the points to edit their values. For our pin, we want it to start at a position of 5 at time 0, go to 0 at 1 second, hold at 0 until 4 seconds, and then return to 5 at 5 seconds. So this is our imposed motion on the pin. We can press OK to all of these windows and repeat the process for our hinge revolution joint. We want the hinge to be open at an angle of 0 degrees until 1 second, then close to 180 degrees at 2 seconds, hold until 3 seconds, and return to open at 0 degrees by 4 seconds. So this is the piecewise angular position function for our hinge revolution joint. Note that Inventor automatically calculates the slope of our function as well, based on our input, and you are also able to specify the slope instead, and Inventor will automatically calculate the ending point, which could be useful in some cases. Now that we have our imposed motion set up, it's time to run our simulation using the simulation player. Again, if you close the simulation player, you can always reopen it by pressing the simulation player button in the toolbar. In addition to allowing us to toggle between construction and simulation modes, this simulation player allows us to play our simulation, and it controls the simulation timeline. Here we can specify the total play duration, which we need to make sure is long enough for our imposed motions. For our door hinge, this needs to be 5 seconds. We can also specify the number of frames we want in our simulation. A smaller number will allow the simulation to render faster, so I will change this from 500, which is 100 frames per second, to 150, or 30 frames per second. We also have the option to play our simulation on loop, but I'll just click the play button to play our simulation once, and everything looks good here. So there we have it, we've created a dynamic simulation. If your motion looks strange, it may be due to an improper constraint in your assembly. For instance, for the angle constraint, the order with which you select parts, the angle you set, and the maximum value input are very important. So if your part doesn't rotate as intended, you may need to go back and adjust your constraint settings. Similarly, it could also be related to the orientation of your joints in the dynamic simulation environment. You'll see that if I switch the x-axis of component 1 and then run the simulation, the motion is no longer correct. So that might be something to look at as well if you have to troubleshoot. In this dynamic simulation, we just imposed motion to our assembly, but you can see in the toolbar that Inventor also has tools for us to apply a force or torque to our assembly for simulation. Even though we won't use these tools in this course for our simulations, we can still use the output grapher to graph our simulation results. We just have to drop down our standard joints and find the ones that we are interested in, then click the drop down on those, and select the checkbox for whatever we want to plot. Here I'll select the position of the prismatic joint associated with the pin, and I'll also select the revolution joint, although its values span a much larger range. If we want to export these plots to Excel, we can click the Excel icon button here, and it will ask us if we want to export all of our curves to a single chart or to their own charts. Since the rotation and revolution are independent of each other and in different units, I'll select export each curve to its own chart so that they'll be plotted separately. Then it will ask about a save value filter, which allows us to specify if we want to export all of the simulation data from every frame to Excel, or say just one point in every 5 or 10 frames in case our simulation was really long and we don't want to end up with a huge data set in our Excel sheet. After specifying the value that we want, you can press OK, and a new Excel workbook should open up with the exported data and a plot that we can then save. In this example, our graph isn't that exciting because we specified these values when we imposed the motion for our simulation, but we'll see in the gear train example that this output grapher is really handy for design verification because we will be able to impose a motion on the input gear to spin at a certain angular velocity, and we will be able to check the angular velocity of the output gear using the output grapher. This wraps up the steps for making a dynamic simulation and exporting the results to Excel, but I do have one very important reminder if you want to share your dynamic simulation assembly file. Remember that you can't just share the assembly file alone. The part files it is associated with need to be shared with it, so you should use Pack and Go to package and zip all of the necessary files together for sharing. To use Pack and Go, go to File, Save As, Pack and Go, and when the Pack and Go window pops up, select the destination folder, then make sure that Skip Libraries, Skip Styles, Skip Templates, and Package as Zip are all checked off, and that Collect Workgroups is unchecked. Then press the Search Now for Inventor to look for all of the necessary files, which should show up in this Files Found box. Then we can click Start and Done, and you should find your zip destination folder in your File Explorer that is now ready for sharing. Here's our last set of troubleshooting tips for our lab lessons that will cover some common pitfalls associated with dynamic simulation and assembly modeling. One common issue is trying to edit your simulation while in simulation mode, which won't work. If your joints are grayed out, you need to return to construction mode via the simulation player in order to be able to edit them. If you close the simulation player, you can bring the window back up by clicking the button in the toolbar. Finally, if joints aren't appearing as you'd expect in the dynamic simulation environment, or the simulation isn't working properly, it might be due to improper assembly constraints with limits or motion constraints, and you can always go back to edit or delete constraints and redo them. You'll notice in the assembly browser that all assembly constraints with limits have a ± in their label, which will help you distinguish them from the rest. Even though you can usually go back and edit constraints later, it is recommended that you resolve assembly constraint errors as soon as you notice them to avoid getting errors on top of errors, which will make it much more difficult to go back and correct. This wraps up this lesson on Inventor's dynamic simulation environment, where we've simulated translational and rotational motion from assembly constraints with limits for our door hinge assembly. In another video, I'll walk through creating this dynamic simulation of the gear train that we previously assembled, which will involve motion constraints and inserting new joints in the dynamic simulation environment. So be sure to check that video out.